Okay, so hopefully now you have a good idea of what basic string scanning and wildcard scanning and those kinds of techniques look like in early malware scanners. So then we sort of upgrade to what we call second generation scanning techniques. At this point in the history of malware, we've got mutation engines, polymorphic and metamorphic malware. We have encryptors and layers of encryption that malware is using to disguise and conceal itself. That proved to be too difficult for our original simple single string scanning techniques, so the scans had to evolve to keep pace with the new changes in malware. So the first attempt is something like smart scanning, where we looked in class at the insertion of garbage instructions or long strings of no ops or reorderings of instructions to make code bodies look more complicated and more dynamic, so that we could generate new signatures. So the idea with smart scanning is we actually strip out from the executable stuff we don't need, right? So we strip out, maybe we have libraries that know what common sequences of garbage instructions look like. We remove all the no-ops, anything that looks like white space. Another technique is to even remove parts of the code body that are referencing variables in the data section, or specifically referencing imported libraries and things like that. So maybe we're only looking at regions of the code that perform calculations, maybe do calls to local functions, not ones that we've imported. The idea is we're trying to distill the program down to really the most meaningful instructions that would hopefully be static and consistent even in a mutated or polymorphic or metamorphic malware sample. If we can do that, we can go a little bit further and basically strip out non-essential stuff, like maybe even local variable declaration. If you remember your assembly, the prologue and epilogue components that we have at the start and end of functions, again, sequences of no-ops. If we can boil the program down to just those meaningful components, we sometimes refer to this as the skeleton. So then we can use strings or parts or collections of bytes out of the skeleton to build more intelligent signatures for malware at this point. Right? This way the scanner is hopefully just focusing on stuff that should remain the same, even if the malware implements a different decryption algorithm every time. There are times where, not for regular users, but malware analysts might want to be able to uniquely identify a sample. When I say uniquely, I mean, say we've got a strain of ransomware that belongs to a particular family, and there's lots of subvariants and versions of it. For a regular user, they don't really care. As long as their AV suite detects that, hey, this is ransomware, I've stopped it, that's good enough for them, and that's good enough for most corporate uses as well. But on the actual anti-malware organizational, research or threat hunting teams, they want to know specifically which version of the malware was this. So in addition to general detection, we need to have mechanisms for uniquely identifying samples. So that's what nearly exact identification means. Typically, it's just going to be using a collection of strings, right? Or a collections of bookmarks and skeletons and strings to build together, a bunch of data that all has to evaluate to true for us to uniquely identify a particular sample. We can speed some of this up by implementing things like checksums or really simplistic hash functions. And when we say hash here, we're not running the entire executable or malicious document through SHA-1 or SHA-256 or whatever. We're taking smaller chunks of the file and using some kind of rudimentary hash function, or even just taking a block out of the file and passing it through a regular hash function. The goal being, maybe I've got a 512 byte or maybe, a 100 byte signature. Well, maybe it's a bit faster if I just take that, do a quick hash of it to something more simplistic that I can compare to a smaller numeric value, and this will speed up the scanning a little bit. An additional sort of nice to have or cool feature you get when you start using things like hashes or checksums is that the hash is a consistent size, right? Regardless of the size of the input that's put into it. So that means the hash database or the anti-malware database can be more efficient, right? It can store signatures that are essentially all the same length, so we get a little bit of a bonus there. We could, in theory, at this point, even move to signatures that don't actually use strings at all. It's just a collection of hashes and checksums at different locations within the file. and that may help us to increase the speed of our scanning a little bit. There's also times where like that sort of near identification is not quite sufficient. We could imagine scenarios where we want exact, like guaranteed identification of a sample. That's just taking more collections and larger collections of ranges, bytes, hashes, checksums, bookmarks, wildcards, like all these things, and layering them together with inclusive statements like, or exclusive statements like ands, right? So we and a bunch of these things together, and if a sample matches all of them, then we're pretty confident that we've identified a unique sample. And again, that's the kind of stuff that a threat researcher or a malware reverse engineer would want to do to make sure that they've got, either a new or an existing sample that they maybe have already seen before. The regular end user AV suites don't necessarily care too much about this. They just want to know if it's a general, family classification. But this does have a use, right? There are people who need this capability, and that's how they would implement, just by chaining together all of the techniques that we've looked at so far. There are times where these types of signatures are insufficient, right? There are structures of programs, there are things that we know that a sample might have that we simply can't express through a pattern or a series of patterns, right? Maybe the structure of the malware is more complex than that. It's too dynamic. So we actually might start to think, oh, I could write a program that would identify this using things like loops and conditions and, like backtracking and all this kind of stuff to help me really identify a particular sample for instances where a pattern or a simple signature is not sufficient to ID it. So that's where they sort of invented this concept of algorithmic scanning, where you would write a program that, again, would just use regular programming structures to parse through a file and apply a bunch of rules and logic to determine if it was a particular sample of malware or not. Initially, the first versions of this were kind of hard-coded using particular instructions for specific architectures and specific OSs. And obviously that makes your code really difficult to port, right? All of these signatures would essentially have to be rewritten for different OSs and different architectures. And that becomes really complicated and a nightmare to manage. So what they did was create a sort of a domain-specific language, or a DSL, that just really contains instructions that are focused on describing the types of stuff that a malware scanner would need to look for. So things like seeking through the file and reading and comparing would sort of be the primary instructions in this domain-specific language. And they also decided to make it sort of more portable, so that it used something like a Java virtual machine style VM, so that the code was portable. You could run it on anything, and the description of the algorithm for scanning for a particular malware sample was really high level. Obviously, because now we're, rather than looking for a simple substring, we're basically taking every program and feeding it into an algorithm to search it for the presence of malware, we're going to incur a lot of slowdown, right? So algorithmic scanning required another sort of branch of features or some rework to sort of speed it up. So one of the things that was implemented was the concept of filters. And if you've ever configured like a regular AV scan, you've probably seen filters used, or that you've had the ability to configure these filters yourself. So this would be like, excluding folders that just wouldn't contain malware, or excluding or including certain file types, right? Because most malware, kind of needs to live in a file that has some form of executable code, whether it be a compiled executable or something like a PDF. That it can have embedded JavaScript, right? So we would exclude files that don't have these executable components to them. You could include filters to search for maybe the presence or absence of certain file headers, or maybe if you know that a bunch of samples include like a new code segment that has a strange name to it, right? You could filter by that. You could really filter by any piece of metadata that you want, like file size and file location and things like that. So reducing the number of files we need to scan is a way to speed up algorithmic malware scanning. Other things we could do, if you recall from our analysis of like cavities inside executables, right? We were looking at the section alignment, and really we saw how much empty space there was there, how many long strings of null bytes or zeroed out bytes. And it turns out that there is kind of a general ratio, like it's something like 30 to 40% of that space ends up being zeros, right? It's really rare that your executable would require exactly as much text in the text section as the section alignment. So it's really common to have a lot of zeros. So, but if malware had found that region of zeros and inserted itself, like one of those cavity viruses we looked at, you would notice that there would be a really low ratio, like well below the norm in terms of the number of zeros in that file. So that might be a filter that you can apply. Basically, the filter would say how many null bytes are in this executable. And if there's like less than, a certain amount, like maybe if less than 20% of it is zeros, maybe there's a cavity virus resident in this executable. One of the interesting things about encrypted code is that you're often going to get long, weird strings of binary that probably don't have a lot of zeros in them. So in addition to indicating the presence of malware, it might also indicate the presence of encrypted data. You can also you can filter by uncommon characteristics in file headers, like data segments being set to writable. You could have that as a flag or a filter you use, right? Other things you could filter by, like even the type of executable, right? Like when you run the file command on a PE file, it'll tell you if it's a GUI program or a command line program. And maybe that these certain sample you're searching for only infects GUIs. So you could filter out all the command line programs. Another sort of more modern malware scanning technique that was developed was a way to scan for encryption operations, so decryptors. Right? So you would scan like the text segment for things that look like decryption operations, which would be really handy, right? So that we could start trying to brute force decrypt the encrypted data. It turns out it's sufficient enough that an algorithmic scanner just finds a couple of static bytes in a certain area to begin its work of analyzing the file using that sort of algorithm that we developed, which is nice to know. One of the methods that can be used for sort of algorithmic scanning on encrypted data is what we call the Xray method. Essentially, it's applying like a lot of brute force operations looking for simplistic encryption schemes, right? So the idea is maybe, something's used an XOR encryption scheme with like an 8-bit key, and it's just XOR'd all of the malicious functions with this combination, and that's the decryption function. So the Xray method would basically be going in and taking large regions of the file and applying an XOR operation with, all 256 8-bit keys to that region and seeing what we come up with. And there's a few other single instruction encryption algorithms like add, right? You can add one to every opcode to encrypt it, and then to decrypt it, you would just subtract one from every opcode, right? So there are some simplistic mechanisms that we can sort of brute force to discover if we find instructions. We know we've found an instruction when we perform like a long sequence of decryption and we have a few things that will parse out as real opcodes, but that's sort of the tricky part about doing the Xray method. It's like, when did I find the plain text? So over on Slate, there's sort of a part 2 of the Yara example that you did earlier. This one actually has you simulating this Xray technique that modern or second-gen scanners can use. Yara, it turns out, can do simple XOR brute forcing. So you'll see on the instructions on the example that you're basically going to apply now an XOR brute force to one of the samples that was in that original collection. So again, go off, do that, and when you're complete, come back, and there's a sort of a third part to finish up this lecture.